Thank you for coming. Um, uh, I'm Jonathan Swan. I'm head of ADR UK data engineering within ONS. And as has already been trailed, this is part of the Research Excellence series, and it's developing data engineering principles for creating research data. So first word about admin data research. I'm sure you all know about this, but I'm going to pop a quick slide in. This is Admin Data Research UK. It's an externally funded program to ONS. So ADR UK pays ONS for our work. And it's part of a UK-wide partnership transforming the wealth of public sector data into research assets and policy relevant insights. That's the stated aim of the research. And as Emma said, this workshop is based on one delivered to the ADR partnership event. The workshop that we delivered to the ADR partnership event covered messy data, complex data, as well as what I'm going to cover today. So this part of that workshop. And of course, this work is funded by ADR UK. Oops, sorry, that's an old agenda, so please ignore that. I've not been well, I didn't update that, but the key point I wanted to raise here was the presentation contains animations. So if you're looking at it in edit mode, or if you have problems reading the text in the animations, then I've repeated the relevant text as hidden slides in a flat and black and white format, and we'll for when we share the slides afterwards, so you'll be able to see that additional content. So first of all, why do data engineering principles matter? I'm a researcher. Why should I care about data engineering? Well, data engineering includes the process and preparation of data to enable users and researchers to use the data. We take the data and make it available for others to use. If we get the principles right, this will enable easy use of the data, consistent use of the data, accuracy both in the data and in its interpretation, and also help avoid error, which I guess is part of accuracy. So this is why the principles matter. This is why we need to get our engineering right to enable this for researchers. So I thought I'd cover a real example. You may or may not know this, but a couple of years ago, I think it is now, the early data from the census was started to be released, the 2021 census. It's worth knowing that in 2011, male was recorded as 1 and female as 2 in the data. But in the 2021 census data, the underlying data, that was reversed, and male was recorded as 2 and female as 1. And because it's got 1 and 2 in the data, it's not immediately apparent what is male and what's female. And so an early piece of research work that was put out had to be retracted and reissued because the male and female got switched because somebody was used to using 2011 data and older data. So that's just a brief example of why engineering principles matter. We wanted to try and avoid that by the work that we do. So as a postulation, my postulation is that data that are intended primarily for research use should be engineered differently than data for other uses. Not entirely differently, but with a different focus. So as an example, standard data engineering practices emphasize efficiency. So that's a balance of processing speed and the size of the data. And that's ingrained in data engineers to work with that view. but I think that data for research use, we should be aiming at making it easier for researchers and favour ease of use over those efficiency considerations. So another example, remember the Millennium Bug? So people often laugh at it because it didn't come to pass. Well, actually, it did in some small ways. So the Millennium dawned, and there was only limited impact on users, but there was still some. So an example is a credit card system experienced issues with machines not correctly processing the cards, ones that were due to expire in the new millennium within the 2000s. Customers were also charged incorrect compound interest, which I'm sure came as a shock to the customers because of issues with the date. And there were many, many, many more that that were actually intercepted before they became a problem due to correction work. One of the disturbing ones was a bug was found in the UK Rapier missile system, and to have a bug in something like that is, kind of disturbing. In this case, it would have prevented launches if it hadn't been fixed before the millennium. And all these issues were ultimately because of the need for efficient data storage. We maybe think less of efficient data storage now, but it's still a concern, and we still, as data engineers, are mindful of it. But it was even more critical back in the past when computing was just getting going, and ultimately people were storing dates as 1999 instead of 1999, with the obvious problem of the Millennium Bug. So that's an example of when sort of over efficiency has caused issues, and it has parallels to preparing data for research, because we need to focus on the research use and less on the efficiency. But you might ask, shouldn't we worry about data size? So I thought I'd do a real example here. We pulled out one of our data sets. It's kind of a medium-sized data set, or small to medium, and it's on pupil absence data. It's used in a large project, the Growing Up in England project, but it's a particular data set within there. The original CSV for those data, kind of the flat version of the data, is 8.9 gigabytes. But when you convert it to Parquet, which is one of the common formats that underpins access in modern systems, that Parquet actually has compression built into it. And when you convert that data set that uses 123 for sex, not the version we produce, but the version 123 for sex, that comes out at, I'll let you read the numbers, but 1.0930 gigabytes. So what happens if you try to make it more usable? Instead of 123, put M, F, and O for male, female, and other. Well, believe it or not, that actually saves data size, and it comes out at 1.0876, but importantly, it saves 0.0054 gigabytes. So it's a very small difference, but it does actually save a small amount of memory, in this case, 0.5% of the file size. And even if you go to go farther, instead of just using MF and O, used male, female, and other in full, it still saves memory on the original. It's a little bit bigger than the MFO one, but it still saves memory, and it's only sort of 0.0016, which is minuscule amounts bigger by taking that approach, but it still saves 0.35%. The point is that by using an approach to make the data easier, it's not going to have a huge impact on data size. So for most of the data we use, it really doesn't matter. It will sometimes save a little bit of money, as a little bit of memory, as in this case, but it really doesn't matter that much. And if you're thinking about the cloud, data size means money. These sort of differences are in rounding errors within the data. So it's better to take the approach that makes things easier than not. So there must be existing principles for data engineering, right? Well, sort of, kind of, you'd think so. If you start Googling for data engineering principles, you comes up with things like this: 7 data engineering principles you should be aware of. You get the point. Data engineering, loads of them, all loads of different principles. So which do you use? Which do you follow? There is no standard at present for data engineering. Not quite. When you do the digging, there are 2 main existing principle frameworks. These are frameworks that are built around software engineering principles. So things like flexibility, reproducibility, reusability, scalability, auditability, lots more abilities on there. They are presented in different ways, but often come back to a selection or presentation of those kind of core software engineering principles, which are all audible and all very good, and absolutely we should be following those sorts of principles in our work. There's also the solid framework. Please don't worry if you don't understand this bit. It is really hard to get your head around, and would probably take you quite a little bit of study to try and figure it out. Essentially, the solid framework is a very technical framework for how data engineering is implemented at a very low level. It is very valuable, it is widely used, but it is incredibly technical. There's what it stands for. As I said, please don't worry about that. For the record, I have put an explanation of what it means in the slide deck, but I am not going to go through it. And as well as those sort of principles, there are the usual helpful acronyms, such as DRY, don't repeat yourself, you ain't going to need it, and keep it simple, stupid, which are maxims to live by, no doubt, but are not incredibly insightful and helpful. So when I started to look at this, I was having to think about what data engineering principles would look like to support research use. Starting on the right hand side on the slide, we do have those very technical implementation principles like solid, which we should abide by, but as researchers you shouldn't need to care about that. That should be technical data engineering doing that in the background, and you really shouldn't need to care about that sort of implementation principle. So I'm not going to cover that anymore on this presentation. And then I've split other principles into delivery principles, and that's principles that are going to help us as data engineers deliver. And you should, as researchers, be interested in those because they will have an impact on the results that you see. And those are the principles that follow those, broadly speaking, follow those data engineering principles. Adapted in some cases, perhaps, but those are the principles. And then on top of that, I thought there should be some user principles, and that is principles that are going to aid the research. So principles for the work we do, for the data engineering, that are going to aid researchers. And we'll cover those a bit more in a moment. But before we go into them, I was trying to think, is there an overarching principle? And I think there is. And you might want to have a think about this and think about whether there should be more of these or whether this should be tweaked. And we can talk about that when we come to the discussion. So as an overarching principle, where possible, ease of use and clarity for researchers should take precedence over other concerns. If necessary, we need to take a balanced view. So on super huge data sets, you might need to worry a bit more about storage and processing efficiency. So a balanced view, but in general, prefer ease of use over other concerns. So it doesn't matter too much if it's not storage efficient, if the data are easy to use. So those principles. So these are the going to start off with these user principles and take you through these. As I present them, have a think. Do they apply? Do we need something else? Have I missed something? Do you disagree with any of these? But these are the principles that I've been coming up with to help support researchers. So first of those is change minimum. So if you're going to make changes to the data, then keep those to the absolute minimum that you need to in order to replicate the data. And that way that you as a researcher can be confident that the data you're getting and seeing and analysing are the data that were recorded. Second principle, add value. So seek to add value to the data. So as data engineers, we can potentially do an awful lot to add value to the data before you see the data. And the way we do that is covered by principles to come. And so the first of those is to add flags to the data. So adding flags is mainly done to highlight issues, but can be done for a number of reasons. And we add flags generally because data are rarely clean. And adding flags can draw attention to issues within the data. So we've used them in growing up in England to try and indicate where we think there's a problem with a matching case where we're not sure that the match is particularly good. And that was an engineering ad late on in the process. Adding flags can save researchers time. If you're constantly going to the data and running a if-then query, then actually we should probably have that in as a flag. And we can also use flags to pull through information that you wouldn't be normally allowed to see, such as identifiable data, names, addresses, things like that. And we can pull through information from that in the form of flags where the originals have to be dropped. So an example we use is around national insurance numbers recorded in the annual survey of hours and earning, ASH data. Those national insurance numbers are recorded manually within the survey, and we know from having worked a lot with the data and doing lots of research on those raw numbers that can go wrong in a number of ways. And so we've put flags on to indicate where there's a problem with the national insurance number. So even though you will, as a researcher, you'll never get to see that national insurance number, there'll be flags in the data to say this number that's been recorded is a bit suspicious. and then you can take effective action to say, well, okay, I can probably see why that data case is not joining up, or I want to exclude those cases as you see fit best as a researcher. Moving on, as well as flags, we create derived variables for corrections. So we can correct data, and in line with the change minimum, we would normally put the original data through, or as close as we can, but we can create a corrected version of the data as well. So you can use a corrected version. An example of that is there are various rules you can apply to postcodes that can correct the postcodes. And if we're going to do that to postcodes that you're using, we would seek to put the original and our corrected version. So an example we often cite in ONS is that our office postcode is PO155RR, which is a Portsmouth postcode, and sometimes that might be recorded as P015, and we know that postcodes can't have a 0 in that position in those first two characters. So we can apply a rule that corrects those zeros to an O. And there are a number of other similar rules that you can apply to correct postcodes, and similarly for other data. Moving on, I'm going to pick up the speed, I think, a little on this. Where you have a need for derived variables, so if you're constantly creating a variable that adds interpretation to the data, we should include that go back and include that in the source data, in future versions of the source data, and agree what that derived variable looks like. A noddy but classic example is converting date of birth into age. It's trickier than you might think, actually, if you've ever tried to do that. But we often put age in the data instead of or instead of date of birth, because date of birth is disclosive. So that's just a noddy example of doing that, of putting a derived variable in where there's a common understanding of what that should be. We should also standardize the data. So we have standards in ONS that we are trying to propound for how data look, what they should be like. And if we follow those standards consistently, it just enables more easily interpretability and compare end results if we always apply those standards. Again, back to earlier principles, if we have changed the data to standardize it, we would probably include the original and a standardized version. Coming back to that census example, use meaningful terms. So where possible, use meaningful file names, variable names, and category names. So in that classic simple example, use male and female instead of 1 and 2. That's a little bit of a hobby horse of me, but I think we should do much more of that. It just makes your analysis so much easier and just reduces those risk of errors. And talking of making things easier, we should prioritize easy use over storage or processing efficiency. And that just makes things easier for you. Not many more of these. Again, in light of making things easier, we should prefer the use of simplified data structures. Typically, that means flattening the data, and that just makes it easier to use. It avoids you having to create code to pull data together and create the desired views of the data. So if you don't know what flattening data means, I've got an example here I will cover briefly. If you've got, say, a custom order system with orders, customers, and details about the things ordering, and you've got all that in separate tables, you can actually all bring it together in one table, like here, and that's flattening the data. Storing it in those separate tables is generally more efficient and uses less memory, but it's a lot harder to use when it's split up like that, and you can combine it into this data even if you are repeating data, like Alice Jones gets repeated a number of times when it's not necessary, if you're minimizing it, but it makes it a lot easier. So that's flattening data. That's part of the general principle to make the structure of the data as easy as possible. And finally, consider data views. So where the technology allows, and these days it's more where it's implemented, use views or even multiple views to add value and help the users have the data. So in that example that I just showed, you could have, as a data engineer, we could create that flattened file as a data view, so that whenever you click on it, it pulls the data together and presents it to you in that format, even though all the original data is in those flat files. So that's what data views can help achieve. Not implemented in some systems yet, so it's maybe one a bit more for the future. So that's the last of the user views. Have a think. Have I missed anything? Do you disagree with any of these? These are some of the delivery stuff, and I've explained here why they're important, and they are around those abilities. Reproducibility, reusability, scalability, auditability are all really important to being able to supply a reliable service to yourself as a researcher. And finally, I've added to those availabilities document and share. So document everything, code, derivations, etc., and share that. The amount of times I've had researchers just ask for material that we've prepared and given them to, and we're normally very happy to do that, although it can sometimes take time to do it, and it just helps your life as a researcher. So I'm aware I'm a couple of minutes over, but I am moving into final thoughts. Good engineering for researchers has the potential to be very valuable. As data complexity is increasing, this is becoming increasingly important. Mainly it's just about good engineering, but sometimes different is needed for researchers, and I've covered some of that. And it takes resource to do things well, but we should spend that resource because potentially it can save resource overall. Sometimes that means that we have to put more resource in our end to save lots more resource at your end, at the research end. But I think it's a valuable investment.